Welcome. Today's module will be on structures and will be your introduction to some of the old building methods and materials and some of the building methods and materials currently in use today. We will explore how the old methods of construction evolved into today's modern building systems. Constant through this evolution are the forces of nature on our built environment and the strains these forces put on our shelters. In order that you may learn how to implement new designs and change existing designs during your careers as interior designers, it is important for you to understand what holds up the building that contains the interior space which you are designing. Fortunately for us, the laws governing construction of structures do not change with the passing of time, and these forces are pretty well understood, but generally not by the interior designer, nor even often by the architect. So with whom do you consult? As there are specialists in every field, so too does your field have specialists for concerns as to how to possibly change a wall location, or pop a new window or door into an outside or interior wall, or penetrate the second floor for a new stair to the first floor. You need to consult either the architect or the building's structural engineer. The builder does not know why something he built was specified to be built a particular way. The architect may have only a limited understanding. It is the structural engineer who designs the skeleton of the building's supporting wall and frame and whose understanding is best. You need to have at least an elementary knowledge of structure and structural systems to begin to be able to have a conversation that will allow you to realize the full potential of the design you have in mind, and preferably before you've sold your client on that particular design element. Here is a cartoon of the three little pigs. The three little pigs found out the hard way that the material choices which each of them made affected the structures of their homes: straw, stick, or brick. We know who came out the winner against the force of the wind of the wolf. What is best about the brick and brick construction that allowed it to succeed where the others had failed? What are our best material and method choices for a particular application? Why were those signs posted there? How was the number of people determined, and by whom? During design, the building or room is an amorphous organism, always changing, growing, shifting, shrinking, morphing again, as its size and shape is refined. This requires continual communication between all stakeholders. We've already spoken about the architect who designs the structure's appearance, the structural engineer who helps the architect implement the design by engineering how it will be freestanding, and the builder who brings together the architect's dream and the engineer's disciplined pragmatism. This give and take process continues throughout the design towards a hopefully peaceful coexistence of systems, spaces, and materials. They all know how to speak one to the other, and as a building professional, you need to learn to speak their language as well. There are other designers you will encounter, and you will need to learn how to speak their language too. Lighting designers, heating, ventilation, and air conditioning contractors or engineers, known in the field as HVAC, heating, ventilation, and air conditioning, electrical engineers, plumbing engineers, amongst others. How can we make choices if we don't understand the limits that the structural skeleton and these other engineering and mechanical systems impose upon us? What laws of nature have been put into play by our particular building package that we must respect? How can we make choices if we don't understand the limitations of the materials? We need to understand the constraints within which our materials exist. What are the particular characteristics of a material? What are the favorable forces working to support our design? And what are the dark forces working against our design? Understanding the actual physical forces working against us help us by focusing our attention on being productive. And clients appreciate that. Edith Wharton, an early American novelist and designer in her own right, discussed interior design as decoration which needed to complement the building's essence, space, form, and functionality. As designers, we understand that pleasingly proportioned rooms inspire, and that at our best, we should build and decorate shelters based on our individual needs rather than popular trends. With what do we build structures? We build with materials that can withstand the ravages of nature, time, weather, gravity, physics, biology, chemistry, to name a few. During Egyptian and Roman times, that material was predominantly stone and masonry. The pyramids of Egypt have stood for 4,500 years. Their longevity due to their realization that a thick, strong base was a critical element in building tall. The Egyptians succeeded in building taller than any structures preceding them. With the height of the structures built on masonry walls that increased in thickness as they neared the base of these structures became so monopolized by support walls that it was useless for any other purpose. The material and method of construction topped out. So strength of material is not all that is required. There are many ingredients required. One ingredient all materials must have is elasticity. When stressed, the material must return to its unstressed state. Of course, no material is elastic forever. For instance, if I take a piece of string and I pull on it, I've stressed this piece of string. If I remove the stress, it goes into its restful state of equilibrium. Of course, no material is elastic forever. As the load on it increases, even gradually, eventually the material will break. We can see here in this brick sample the outline of brick failing at the mortar joints. Before it does fail, however, the material may develop a permanent deflection, such as what I just pointed out. It then begins to behave in a manner that is no longer elastic. The appearance of permanent deflection, such as a crack shown in this picture on the right, often provides advance notice that a structural material is in danger of collapse. Rather than trial and error, today's buildings are based upon historical and empirical information. Engineers are able to anticipate and computer model many stresses and aging scenarios that were unimaginable even in the last century. By precise calculations, the essential properties of a structural design and of structural materials can create the essential lines of a construction and a perfect appropriateness of its use. So here we see the perfect appropriateness of the structure on the right for its use as an amphitheater, and the appropriate structure of our human skeleton for the appropriateness of our needs. Structures must be designed to be supportive of static and dynamic vertical gravity loads designated as dead loads or live loads. So for instance, here is a house. We consider that the dead load. It's the object itself with any additions. The live load are the people, furniture, or storage items that go into that house and exert additional stress. On the right, we have two girls. The girls are the live loads. They can come and go. There might be another girl added, maybe another one leaves. We don't know exactly what the live load stresses will be. We can only anticipate what they are. We do, however, know what the dead loads are because they comprise of the weight of all the items that make up the bridge, the bamboo, the glue, any connections. So the weight of the women on that bridge is counterbalanced by the weight of the earth below. So dead loads include the weight of all the permanent building materials, such as roofs, floors, ceilings, doors, walls, windows, skylights, plumbing, heating, ventilation, and air conditioning, I said referred to as HVAC, electrical equipment, vertical access equipment, stairs, elevators, escalators, the structure itself. Here we have a wood structure, a steel structure, and a concrete structure. So the weight of the objects that comprise the structure itself are the dead loads. We can see from this composite slide that the elements of a structure can add up quickly and to a heavy load. The evaluation of loads is a careful and painstaking job. No one wants to fall through a floor because the engineer had made a mistake in assessing the weight of the people expected to be there, the live loads, and objects on the floor, such as furniture, desks, chairs, and the floor weight itself. For these reasons, engineers generally overcalculate to assure a healthy margin of safety. You can see from this chart why we say that dead load weights are knowable, quantifiable, and therefore predictable. For the most part, it is the amount of dead load weight that varies from project to project. These dead loads are referred to as static loads. So here we have a computation of steel weight for pounds per cubic foot. That's a box 1 foot wide, 1 foot tall, and 1 foot deep. So we can calculate, knowing the quantities that we expect of the materials in our design to be calculated, multiplied by the pounds per cubic foot, and we can calculate the loads that are going to be expected to bear on the ground or the soil below that building in order to make sure that those soils are sufficient to resist that load. If in designing a floor you would only consider the live load, you would be forgetting the heaviest of all the loads, the weight of the floor itself. This again is called a dead load because it cannot move. It is always there and it is very heavy. Another type of force that we can talk about are dynamic forces, which often produce cataclysmic results. Here we see where a meteorite hit the earth and exploded and acted cataclysmically against our ground. We have all probably heard stories of fraternity houses that have parties where they overload the deck outside while the kids are celebrating, and they've overloaded it with too many people. The deck was not intended to support perhaps that many people, and it collapses immediately, dynamically, and cataclysmically. So dynamic forces are different from static or dead loads because dynamic forces, unlike static loads, which take place gradually over time and eventually outweigh the resistance of the object in which they're bearing, dynamic forces are often sudden and unexpected and produce drastic results. Another type of live load that you may not have thought about is snow. Snow comes in the winter, we don't have it in the fall or the spring or the summer, so it's a live load, it's transient. One minute it may be there, the next season it's not going to be there at all. So the building codes require that we consider this as a live load, and the building codes, which do dictate much of what our design will allow, even though we want to use our imagination to the fullest extent, our imagination is often reined in by the limitations that the building code imposes upon us. So snow is one of them. We need to design a roof to support when there is snow. We're okay when there's no snow, but when there's additional load or maybe somebody working up there, walking around, then we need to make sure that the live load is taken into account. I can also say that live loads are movement generally across a surface, maybe a car across a second floor parking garage or a grand piano across a stage. Maybe the people are walking or partying upstairs. So live loads act vertically downward, as we said, but also generally in a forward motion. Live loads also are the people and the furnishings, whether it's classroom furnishing, office furnishing, any type of furnishing, people, anything that comes and goes, that's the live load. So this chart of live load allowances is typical for what you might expect to find in your local building code ordinance. Not in the jurisdiction of where your office is, but you need to read the building code, I would say at the beginning of a job, of the jurisdiction in which your job is located. So for instance, this reads that if we were doing an office, we would need to design our structure to support 100 pounds per square foot. So they're figuring a 12 by 12 square that I'm standing on needs to support of at least 100 pounds per square foot. And the person next door, and the person next door. Every square foot, 100 pound support. That will take into anticipation many of the different loads that we can think about. So that will often be seen mounted on the wall, but you do have to remember that the more pounds per square foot that your building needs to support, the heavier the structure most likely is going to be. So it is another important reason, among many, to always consult the local building code. So here we have a gallery. Maybe we have a couple of 5 people come during the day to view the show. At night there might be an opening and you could expect 200 people. So the building code requires that for every person in the space, there is a minimum allowed area for circulation. So if I'm standing in that gallery, the building code might say, I need to be allotted 7 square feet of my space. The person next to me needs 7 square feet for their space, and the next person needs 7 square feet, and right down the line. So if we take the size of the room and divide it by that 7 square feet, we can find out how many people will be allowed to legally occupy that space. That's the number that the building department will then post on the wall and say, not to exceed 49 people in this room. Your client may say, wow, 49 people is not enough. I wanted 200 people to be visiting in here. Well, you need to increase the space that your client has allocated, and you need to let them know that their expectation cannot be met with the parameters that they've set. Other loads calculated by structural engineers include dynamic loads that I mentioned, and one of them is wind. So wind is a lateral load coming from the side, and it's pushed this house over. The house wasn't able to resist the amount of wind being placed upon it. All of a sudden, it fell over. Maybe in the past the wind had never achieved the level achieved that particular day. I exceeded the limitations of the structure of the house, and the house fell over. In a low-rise structure, we do have lateral loads such as wind also. The load on a low-rise is not as great as the wind load on a high-rise. The higher the story of the building, the more wind is pushing against it. So the structural engineer takes that into account. Other types of loads that we might have that are dynamic might be earthquakes, explosions, moving equipment like forklifts or bulldozers. And to resist those loads, the engineers often have their own bag of tricks. And in this case, we're looking at the city court building, and there's an effective way that they use to restrain the building from movement and keep it in a state of equilibrium or rest. That way is by inserting a pendulum at the upper levels, that when the wind against the building is pushing in one direction, the pendulum swings in the opposite direction and to counteract that lateral load, and the building tends to stabilize. So much like our own skeletal systems, when pushed in a direction for which our joint was not intended to be pushed, stress occurs, and we may end up with a strain, a break, or worse. The same occurs on a building structural system with similar results. Structural stress is manifest by tension or compression, much like our own stresses. So in this example, people are pushing against each other. That means they're in compression against each other, and they are pulling against each other. In that case, they are both pulling and they are in tension. What we want to do in cases of our structures is to release those stresses or minimize those stresses or equalize or put at rest those stresses. When a material is pushed together, the result is compressive stress or compression, resulting in a failure depending upon the type of compressive stress that material had undergone. And equally, when a material is pulled, the result is tensile stress or tension. So here we have a tug of war. If the two teams pulling on that rope pull to an extent that the rope can no longer resist the amount of load being exerted on it, well, the rope will fray. That means that we're starting to see failure, but we don't have failure yet, but we know something has to be done, otherwise it's going to be failing. And if they let up on the rope, it won't fail, but if they keep pulling and tugging hard enough, it's going to break and will fail. The most common type of structural system is called a post and beam. And I like to liken that to a table, where the table top is a floor or a roof. It's supported on 4 sides by beams, and the weight of that tabletop or floor or roof on those beams is transferred to the legs or the posts and transferred from there down to the ground. So the ground is resisting an equal and opposite force that is being applied on it from the weight of the table. Now, that table is the dead load. If we add a fruit bowl or a book on there, then that's the live load, increasing the load that its earth needs to resist. So beams are the horizontal elements that span an opening and are supported at both ends by walls, columns. The posts we can also refer to as columns. So here we see beams out of wood sitting on a column. Here we see steel beams, some more wood beams. We call these joists, which I'll talk about in a few minutes. And the restraint on that beam, either by columns or by walls. So vertical loads are carried to the ground by the columns I mentioned, also called posts, or by walls that also typically provide vertical enclosure. So here are the posts or the columns, and infill within those posts are garage doors, man doors, windows, other things, or types of wood, gypsum board, sheetrock, those elements which enclose the envelope and make the interior watertight. Here we have a clear delineation of the beams sitting on columns, all being transferred to the ground, but the ceiling is filled in with the floor from above, and the exterior walls are filled in with insulated partitions, windows, and doors. So columns carry the vertical loads to the foundation in the earth. Therefore, it is very important to understand the nature of the soils on which the building's foundations will sit. Soils vary greatly from area to area, even in areas of close proximity. So it is extremely important to understand the intrinsic nature of the soil type. Soil types can vary tremendously as to their capacity to withstand loads. So here are some samples of columns. These are columns of stone, columns of wood, columns of concrete, columns of steel. They carry the vertical loads to the foundation we have set in the earth. Those columns are sitting on our foundations in the earth. Therefore, it is very important to understand the intrinsic nature of the soil type. Soil types can vary tremendously as to their capacity to withstand load. So what do? We're going to call the soils engineer, and he's going to come out with some equipment and test the soil and find out what type of soil it is, and find out what the bearing capacity of that soil is, and what needs to be done to either to increase it or augment it. So again, another stakeholder in the team that we need to bring to the table when talking about new building construction. So again, Newton's law of equilibrium comes to bear. Here we see a building structure. It's lighter at the top because it's not resisting any stories above it, the weight of any stories above it. Heavier at the bottom because it's got all those floors above it bearing down on it. And then transferring to foundations, which the soil in this case wasn't satisfactory enough, so they insert piles or casings down to solid bedrock. In Manhattan we look for Manhattan schist. It's bedrock. It's the most compacted earth material that we can have. It goes massively into the ground and pushes massively back up on anything trying to force its way down. So in other locations, maybe a house, we have short footings that go down only as far as necessary to reach virgin or undisturbed earth, and that's earth that's been compacted over millions of years, undisturbed, and has achieved its maximum compression, and any load that we add on to it is most likely going to be resisted. So we discover that compacted earth generally by, again, taking soil samples. Maybe you take a backhoe, have your inspector, your soil scientist there on the job, looking to find out when there's no longer disturbed dirt, like fill that's been brought in from somewhere else, until you get down to undisturbed earth. And we want to also make sure that that's below 4 feet, because 4 feet is, in this area at least, is the frost line, so there's no heaving and thawing of the earth below where the footings are. Otherwise we'll have the building going up and down seasonally perhaps. So here's a familiar situation perhaps. The Tower of Pisa, the weight of the tower exceeded the bearing capacity of the soil below it. And nowadays the soil and the tower have been stabilized by special engineering methods, but this is the consequence of not understanding the full soil bearing weight underneath our structures. Right here we have a crack in the concrete, a sure sign that something structurally is happening. We don't necessarily know what it is or how to solve it, but we say to our client, I believe this is a sign of a bigger problem which you need to have investigated in order for us to resolve and have remediated before you would begin your new project of designing the interiors. This is emblematic of some other issue that I'm familiar with observing, same as cracking sheetrock or plaster, but I'm not the team member that can help solve this issue, but we should speak to them and get it rectified because this is a sign of something imminent. Here we have something more cataclysmic, implosion of the building because the soil underneath sank, and here's the settling of a building sinking into a sinkhole. So such is the situation we often hear about in snow conditions where the roof collapsed because the columns supporting the roof or the roof itself have not been designed or built strong enough to resist the weight and gravity load of the snow depth or wetness. Fortunately, these are the exceptions, with the well-designed structures that are generally built with good materials being the norm. In this case, we can see a test of concrete strength being performed on the left by a lab test that was done on some concrete poured on a real job and tested after 28 days, which is when concrete achieves its full strength, so that we make sure that the contractor did not shortchange the owner with the formulation that the engineer had specified to meet the requirements of the loads of the structure. In other words, some unscrupulous contractors might take shortcuts and therefore jeopardize the structure of the building. We don't ever want to see that happen. Sometimes an unscrupulous contractor will add water to cheapen the concrete. Of course, with more water, it's not going to achieve its expected strength. So we do check concrete while it's being poured on a job in little cores by an independent contractor who takes them to the lab and tests them for conformity with what the engineer specified. If it doesn't meet expectation, then there's every right of the owner to have that contractor remove all of the concrete on the job for failure to meet specification and then failure to be able to perform in the expected manner. Some of the other implications that we talk about, yeah, the concrete is going to compress probably imperceptibly, but when the load is removed, it will return back to its original state. Another situation where you might have too much compression could result in buckling. You can imagine that increased buckling here would eventually result in failure of that column. More load, more buckling, warning signs, then finally cataclysmic collapse. So we hope that those stresses, when relieved, have that object, because it is elastic, return to its original position, state of rest. So when we talk about columns, we need to discuss the slenderness ratio. It's the means that we use to assess the strength and stability of a column, and it's expressed as a ratio of length, L, over D, diameter. It's important to us as designers because we want to be efficient in the construction of our skeletal structure. So we can have steel columns which, according to the slenderness ratio, need be only 1 foot wide to go 50 feet tall. That's a good height. Before we had that, we had this type of high-strength steel. We had wood. We still have wood, but we have wood, and wood can only go 30 feet tall for the same 1 foot diameter. And then in antiquity, they generally had stone, that was the building material. They could only go 15 feet tall with a 1 foot diameter piece of stone, right? 2 feet tall, they could go 30 feet. So I think you get that there's an economy to proportion and cost based on the slenderness ratio. So that's important to us as designers to know. So have you ever pulled on a rubber band to put it around your wrist or remind you of something? You stretch that rubber band into a state of tension. Here we have some examples again of tension, the tug of war. This is a well with a bucket on a string, and when you pull up on the bucket with the water, there's tensile stress on that string or that rope. Cables such as on a bridge hanging from some more major cables, those are in tension. They're supported by an opposite weight, the weight of the roadway below with all the vehicles on it. And of course we have tents. Tents are fabric pulled tight and taut in order to be supportive of themselves. If you can think on the most microscopic level, the material that I've been talking about that performs well in tension are fibrous materials. So here's a string, I'm sure you know is made up of many fibers. Steel is a fibrous material. Rope, again, fibrous material. Anything that's not granular, I call fibrous. And fibrous objects are good in tension. If I tie a weight to this rope, the rope is supportive of that weight. Right? So fibrous things are good in being pulled on. They're supportive in that fashion. They're not good in compression, right? If I push this together, there's nothing structural now about this string. Can't support anything. Tension, compression, no. So take a short length of string, cable, or rope and try to pull on it. You can see that that's something strong to be reckoned with. And then push against it or push it together. It's very bad in compression. It has no supportive value at all. So I just want to return for a second to the slenderness ratio that we spoke about earlier. For instance, many people like the delicate appearance of Shaker furniture, but it looks too delicate to be actually able to support the weight of somebody sitting on it. So it is. The legs are just too delicate and spindly. So as a remedy to that situation, the Shakers added what we call stiffeners between the columns and stiffened and gave that chair structure more stability. So a tall, spindly column trying to resist the weight of a heavily loaded floor above it is similar to this tabletop. We have the tabletop, or it could be called the floor or the roof, supported by beams on four sides that are sitting on columns, these in this case slender columns, that are sitting on the ground, and the ground or the floor is exerting an opposite and equal force back upon that table. But without these stiffeners, if the legs look too slender to even just support the tabletop itself, let alone food or other things that are put on as live loads. Beams generally are the supportive system for smaller framing members, which in turn hold up the roof beams called joists. So here we have some vertical framing members. These could be called beams, but because there's something larger that's also a vertical member, we call this the beam, and we call that a joist. So joists and beams are synonymous depending on the hierarchy of the structural elements themselves. So here are some joists framing into a larger beam. In this example, we have the beam being deflected by a load placed on that floor or that tabletop above, restrained on both ends, either by a column or a wall. These are called restrained end situations. And here is an unrestrained situation where the beam is sitting only on one wall, perhaps one column, and the rest of it is cantilevered out, much like a diving board. So that's an unrestrained end. So as I said, beams and joists are sometimes casually used interchangeably, but really beams are generally the heftier or weightier of the two. So here we have joist and a beam. We have joist and a beam. We have joist and a beam. It's the same nomenclature whether it's wood or steel or concrete. So the beams are sitting on columns. And columns and beams respond with tension, compression, and also a third reaction called shear. Here you can see an example of shear in a failed column. The column sliding past itself in the same plane. So this part of the column and this part of the column are sliding against each other, failing against each other in the plane, and that's called shear. So we talked about buckling already, we talked about compression, and we talked about now shear. So the important takeaway here, this is a shear failure where the weight of the column was able to repress the weight of the floor at itself, but the floor was overloading where there were no columns, so that collapsed around the column area. So the shear is happening at the point where the tension and compression are out of balance. Normally we would have an area right in the center where there is no stress because the compression and the tension counterbalancing each other. If they didn't counterbalance each other, then you would have this type of sliding past each other or failure. So if you can imagine, because I don't have an example of this, a beam between two columns with a load exerted on it, and a magnification, these forces are like this, that the bottom fibers are being pulled apart in tension. The upper fibers are being compressed together as it's bent. And in the center, those forces equalize, and that's where we have something called the neutral axis. Now, the neutral axis is an important element for designers, and I'm going to tell you why. But I want you to make sure that you understand this example, that the only thing that's doing any work for this in this beam are the outer edges. This part in tension because the fibers are being pulled apart, this part in compression because they're being pushed together, and where they meet in the center, there's no stress at all. So as I hinted, the secret of the neutral axis holds design possibilities for concealing things we don't normally want to see in our rooms. So again, mathematically, you can see that there's a load at the top of the beam, a load at the bottom of the beam, and in the center, those stresses equal out. So what is the implication for that? Well, the implication is we can cut away some of the material towards the neutral axis. We can now run our mechanical systems and other things perpendicular to the structure within those beams and not compromise the structure itself. Of course, we can always run in the cavities parallel to supporting structural systems, but without being below the ceiling height or the structural height, cutting into the room with soffits or just leaving the equipment exposed. We could always run between the cavity space along and parallel to existing joists or beams, but perpendicular. Now we are able to run ductwork and wiring through a portion of those beams so that we don't have to create soffits or have things underneath the floor to under framing height, so nothing's interrupting our ceiling plane. That's a good thing for us as designers. Now, of course, our engineer has to tell us how much around that neutral axis we can toy around with or play with or remove. We don't take that on. We don't take that question on ourselves because some of that area, of course, is needed for structure. So structural systems are engineered to create unique characteristics of the building's design in a collaboration, as I just said, with the architect and the engineer and yourself. So how will the interior design modifications fit into those hidden structural restraints that only the engineer knows best? So here, someone came up with the idea, well, if we only need the top and the bottom for the structural contributions of that beam, then we can minimize the center. We can now get rid of as much material as our engineer allows us to, and someone came up and with the idea of a truss. So a truss works only at the top and the bottom, and the center is only holding those two edges together. Inside we can run whatever, as I said, pipes, wiring, air conditioning ducts. Whereas typically when we were framing homes, we used standard lumber harvested from the trees that were cut to a manageable size. Maybe a couple of people could carry a heavy wood timber, lift it into place. But nowadays, with the knowledge that only the top and the bottom are really doing the structural job, well, someone decided we can cut away a lot of that lumber. Now we can make the lumber lighter. That means it's going to be less costly to transport, less fuel, less tire wear, and it's going to be easier to install. Whereas maybe you needed 5 guys to lift a heavy beam up before, maybe you just need 2 guys, 1 on each end, to lift up a piece of engineered lumber. And this engineered lumber is actually stronger than the harvested lumber because of the elements and the adhesives that are used in this portion, in the center portion, which are holding the top and the bottom together. The top and the bottom are called the flanges, and the bit holds them together in the middle is called the web, and that's true of engineered lumber or steel. So it's a good vocabulary to know. Flange, web, flange. And as these flanges got thinner and smaller and stronger, we can now span longer distances. Whereas a piece of lumber, maybe a big piece of lumber would span 15 feet from wall to wall or wall to column. And we might end up with a column in the middle of our room or in the middle of our basement. Well, with the engineered lumber, a piece of that, perhaps the same depth, can now span 20 feet. So we don't need necessarily an intermediary support. We can have what is called a clear span, whereas previously we might have had something in the center of our room interrupting the open plan. So some of those equivalencies are in this chart here, that you can match joists and trusses against each other, see what spans are available or possible with those different types of framing members. And also those are important to know because they establish the grid of your structure. The structural grid is imposed upon everything that you'll do in your design. Whether you use that grid or work against that grid, it's always going to be there. So the spacing of structural elements gives an organizing pattern to the structure, and you might use it for your walls, to organize your walls and partitions. Or you may not. You may choose to ignore it and work off of that grid. But in any event, the grid is going to be there because it's needed structurally. You can see in this case a parking garage level with the columns spaced where they need to be to support the building, but it's important to understand that there is an organization to the building which you can use as a benefit or a contrast. So as we talk about the structural materials, this is a slide that shows what those materials are that we discuss in this course. We have concrete, we have steel, we have reinforced concrete, we have wood, and we have masonry, stone, and brick. They're all measured in pounds per square inch. So when we talk about the resistance to tension and compression, we're talking about the measurement of a pound per square inch. 1 inch by 1 inch. How much resistance they have in pounds per square inch. So getting a little more specific about each of those categories, we're going to start with stone, brick, and masonry. I want you to think back to visits or pictures you've seen of antiquities. And what are they most often made out of? They're made out of granular materials that are excellent in compression. Stone, brick, or masonry. Granular as opposed to fibrous. So granular materials are the ones that are good in compression. We said fibrous materials are good in tension. So stone, brick, masonry made up of clay or sand, stone or aggregate, and cement. Those are granular materials, grains. So they're good in compression, but they're not good for beams which need to span and stretch along their bottom edge in tension, which they are not good at resisting. So we saw earlier beams that were restrained on both ends. The tops we said were in compression and being pushed together. The bottoms were being pulled apart. And when you have a material that's not good in tension, it's not going to be good as a bottom part of your beam. So granular materials, bad in tension, going to start to fail, crack, and ultimately collapse and disintegrate on the ground. So masonry used in antiquities have a lot of surviving examples of columns, because columns are granular, stone, brick, or masonry. They're granular, they're being compressed, and they're good that way, and so they withstood the ages. But the beams, because they had an element where they needed to be in tension, but they didn't perform well that way, failed and fell to the ground and basically disintegrated. So we've seen a lot of columns, but we don't see many structural beams. So because granular material is not good in spanning, we have very closely spaced columns in antiquities, right? So not very welcoming, kind of hard to find where the real entrance is. Over time, through trial and error, which is how we've evolved to current materials and methods, through mostly trial and error, collapse, trial and error again, collapse, trial and error, success, build upon that success, collapse, build upon that failure until we succeed. So with this method of construction failing the test of time, someone came up with another idea. Someone came up with the idea of arches. We could have a span that now is greater than what we could achieve earlier and more welcoming. So in fact, arches are known as welcoming elements into a castle, into a city. We have arches of triumph. So by experimentation, someone developed this arch idea, and arches are the compressive structures most commonly used today to span large distances. They came into existence around 100 AD during the Roman era of bridge building. It's very supportive of weight and long span. So it was a good use of compressive granular materials, which they had. So you can think of an arch as consisting of two halves that lean one against the other at the keystone. So here you have a load, maybe a wall up above, with the load, maybe the aqueduct up above, exerting pressure down on the arch exerting pressure outwards, and as it exerts the pressure outwards, it's also thrusting outwards. So in order to restrain that load, we need a resistance weight at the bottom of each leg, which we call buttresses, to keep that from flattening out like a pancake. So thrust is a new term of force they had not yet encountered. So here's the load, here's the arch, it's thrusting out in either direction. It's no longer in equilibrium, but we can restrain it by creating the buttresses. It's restrained, has no place else to move, so it stays in place. So we have a larger span, now we have a structural element that allows that wider span. So as I discussed before, in this case too, we have for each force applied to the building an equal force opposing it. So here's a little cartoon sketch of a cathedral. You see the arches. It can be decorative and taken advantage of that way, and most prevalent in Gothic cathedrals. Here's a different type of buttress. This is a retaining wall. There's a large amount of earth on the other side of this wall, exerting a lot of pressure on that wall itself, but to restrain that wall from flipping over, we have created perpendicular buttresses to keep that wall in equilibrium. So as time passed, we have skilled masons, they became master masons. We had skilled craftspeople who became builders. We had skillful builders who became master builders, and master builders, they became architects, and architects and scientists became engineers. So we have this whole process over time of individuals adapting their skill set to modern or more modern technology, along with advances of materials themselves. So here, someone had the idea, well, we'll create that arch, we'll add the buttresses, but let's make the buttresses open. So now we have a more expansive room that we can meet in or shelter in, allowing some of the spaces within those roof areas to be opened up. So now we can bring light in, we can have rose windows, we can bring this structure to a more airy state, a more heavenly bound state, more lofty feeling, so well adapted to churches and other religious institutions. Not only could you go taller and lighter, but you could further expand that geometry. So you could have an arch, an arch, an arch, and an arch, and now we have a great expansive space that can all now shelter a greater number of people. But we have the arches working against themselves, so this arch and this arch equalizing the thrust against each other. This arch and this arch equalizing the thrust against each other. And then the guy at the end, he needs a buttress, so it doesn't all go down like dominoes. We can even grow that geometry three-dimensionally and create a vault. And we can grow even more by going out in a separate or two directions. So we have now a groin vault and other vault shapes that can be built. We can even take that same dome shape and twist it around its own axis 360 degrees and create a dome. So the Pantheon is a dome. We have an arch leg meeting up with the arch leg on the other side, swiveled 360 degrees, and we have a beautiful dome shape. There are other type of domes, such as a geodesic dome, not made out of arches, however, made out of triangular elements called geodesic polyhedron shapes. So when considering structural materials, we need to consider what is the appropriate material for the type and use of the structure or the interior. What are the unique characteristics of the material which makes it well suited for the application at hand? The 20th century architect Louis Kahn asked the question this way: what does a brick want to be? Concrete is another structural material. Because it's granular, it's very strong in compression. Approximately 2,500 pounds per square inch is its working compressive strength. Here's another test being done on a concrete cylinder to see at what stress level it will start to fail. So here are some examples of concrete. This is concrete arriving at the job in the truck. Here's a gentleman pouring the concrete in place. The inspector from the third-party testing lab is going to come and pour some of that concrete into one of those cylinders, take the cylinder back, let it dry for 28 days, and then subject it to the test that you last saw in the previous slide. You can see this is a cross-section through concrete. You can see the grains of sand, the grains of stone or aggregate, and the granular cement that is mixed in there. With recent advances in concrete technology and special admixtures or ingredients, today's concrete is a superior compressive material where compression is the only stress at work. Reinforced concrete is a very good and inexpensive material because it uses a large amount of cheap concrete and a small amount of expensive steel. And what is happening? These steel rods, called reinforcement bars, or steel mesh, single sheets of steel coming in a grid, are inserted into the concrete where the engineer has anticipated the tensile stresses will appear to fortify the concrete with the tensile strength of the steel. Thus the name reinforced concrete. And once we are able to do that, we are now able to create fantastic new shapes that could never have been executed before the invention of reinforced concrete. Also, reinforced concrete building is usually safer against fire than a steel building because the concrete is itself a good insulating material and protects the steel from melting for a long time before the steel would lose its strength and melt. Here's the reinforcing, again, being inserted within the areas that the tensile stress will occur in the concrete, and some fantastic new shapes that reinforced concrete allow us to dream and build. So at normal temperatures, steel is very strong, but if a fire develops in a steel frame building, the columns and beams, even if they're covered with fire insulating material, may get hot, and if the temperatures rise above 700 degrees Fahrenheit, will lose their strength. Here's a steel building. This is the building no longer exists. It's the Penn Station building that was taken down in the 1960s. These are some shapes that structural steel comes in. We have here tubes and pipes. We have beams. We have lintels, channels, many types of steel forms available to us. So remember, granular materials are strong in compression while fibrous materials are strong in tension. Here you see some steel cable. On a microscopic level, you can see that it's more fibrous appearing than granular appearing. Here is some steel that either was not capable of resisting a compressive load on it or melted because it achieved a temperature higher than its ability to resist. Steel frame buildings are constructed with a structural framework of prefabricated elements calculated and milled to support the specific loads of the finished building as determined by the structural engineer. The steel components are shipped to the job site where they are joined together by welders and other construction workers. Here's a gentleman using a mechanical fastening device to join a beam with a column. So a further evolution of these structural materials and methods resulted in what is called a curtain wall. It's the skin applied on the outside of the structural skeleton, much like our own skin, protecting our internal organs and our skeletal system. The curtain wall is the outer weather-tight wrapping that keeps us cozy, comfortably sheltered. The curtain wall and the structural skeleton are independent one from the other. Lightweight steel framing is different than the steel framing I've already spoken about. The steel framing I spoke about is very heavy material, very heavy gauge, thick material. This is lighter. This is more akin to wood framing that you might use for a house. It is heavier than the steel that we use to create interior partitions, but up to about 9 stories you can build with lightweight steel framing. The pieces are delivered to the job on a truck, and it's assembled by a number of people using screws or other types of mechanical fasteners. Some houses are built out of lightweight steel framing, but most houses are still built out of wood. Interestingly, it takes about 25 old-growth trees to build a 2,500 square foot house, compared with 10 recycled automobiles for the same steel framed house. Lightweight steel framing materials contain an average of 67% recycled steel, and steel is 100% recyclable. So in these last 2 statements you can understand that this is an ecologically friendly building material. So as a comparison with framing a house, this lightweight steel framing is 50% lighter than the wood. This in itself presents a challenge to the structural engineers because of the potential for severe stresses on it. Nonetheless, lightweight steel framing has proven to be a very versatile framing system, and as I said, sometimes you can go up as many as 9 stories now with this framing system. It can be integrated as well with some wood framing. Speaking about wood, I want you to think back to the oldest structure you have visited. What material was it made from? Chances are it was not wood. Wood is susceptible to dry rot, which is water, air, water, air, water, air. Susceptible to wood-boring insects such as termites. It is flammable, so for these and many other reasons, we don't see many very ancient wood structures surviving to today. Wood framing construction, the old homesteaders often harvest the timber and stone for their structures from their own property. You want to build your home, you had your piece of land, you'd harvest your lumber right from the trees on your property, maybe build the foundation from the stones gathered on the property as well. So before the Industrial Revolution, you would have gathered all your materials locally, probably used wood joinery to put the parts and pieces together to build the house frame. You might also have been lucky to get a few nails from the local blacksmith. It was laborious, time-consuming, not the best use of the blacksmith's time. So when the Industrial Revolution came and mechanization began to proliferate, someone started producing on a mass scale nails or other types of fasteners that were needed. People were harvesting the lumber in forests and then shipping it to mills where it was sawn into lengths that were usable sizes that could be shipped to the job site or to the distributor, and then a housing boom started to take place. So as we mentioned several times, the development of building systems has been an evolutionary progression of techniques and materials. So just in closing, but as a related topic, I want to talk about the principle of designs as concepts used to organize or arrange the structural elements of our design. One of these principles is called proportion. Here you see some columns that to our eye appears too thin, they're going to buckle, the building's going to collapse, while at the same time this structure looks too squat and too heavy and out of balance. As designers, we feel there's something intuitively improper about the appearance of those structures, whether it's the structure itself, whether it's the physical components, whether it's the aesthetic components. But here we see what we can call a unity, unified proportions, unified attractiveness. So there's a relationship between what we perceive as attractive proportions and what is structurally efficient. This looks right to our eye. It's proportionate and it's effective and looks pleasing. I hope we have come to appreciate getting under the surface and returning now to authenticity in design. Structures give order to life. So too does structure give order to buildings. Structure informs the aesthetic. So here we have a wood cathedral soaring to the heavens and open to the sky. Here we have the Pompidou Center in Paris, where the structure of the building is actually on the outside and everything is happening within that structure. Where form is true to itself, and as the early 20th century architect Louis Sullivan expressed it, that form follows function, or more accurately, that form ever follows function. Form follows function is a principle that became associated with modern architects and other designers of the early 20th century. The principle expressed the belief that the shape of a building or object should be primarily based upon its intended function or purpose, that its support structure should be visually obvious, and that there is no place for decoration and ornamentation to disguise the design. The articulation of structure is as important to a room as it is to the building itself. William Morris, also a designer, said, "Never forget the material you are working with, and try always to use it for doing what it does best. The special limitations of the material should be a pleasure to you, not a hindrance." Thank you.